So in today's video, we're going to look at chapter 7.4, which is the singular value decomposition. This is the last topic that we're actually going to study in this course, and it's actually a good setup, particularly for those of you going to grad school. You'll use this concept a lot. It's used a lot in coding as well, when they try to do modelling, mathematical modelling. So it's actually a very useful topic. What I want to look at, we've looked so far at when we've got this square matrix A, and we've decomposed it into these matrices P and D, okay, such that A is equal to PD, P inverse. That would mean, if you can do this, that would mean that the matrix A is diagonalizable. However, if A is not necessarily square, you actually can still decompose it into some form of these matrices, but instead it's going to look like this, and we're going to talk about what U, sigma, and V are later on. First thing I want to look at is looking at eigenvalues, because that's kind of like the fundamental part of singular value decomposition. When you have a symmetric matrix, so if A is a symmetric matrix, that means that A must be square. Then you know that you've got these unit eigenvectors, okay? You can find eigenvectors of A, and you can go ahead and normalize them, and not only can you normalize them, they actually form this orthonormal basis for Rn, okay? So you can go ahead and find those when you have a symmetric matrix A. So because you can find these unit eigenvectors, that means that if I took A times one of these eigenvectors, we know that A times x would equal lambda x. Multiply that out. Magnitude of x is just 1 because it's a unit eigenvector. So we get this. What that tells us is that if we have this eigenvector x, okay, this unit eigenvector, that is associated with one of these eigenvalues, okay? The length of the vector A times x, this will give me a vector. The length of that vector is just the size of lambda, okay? So if I take the absolute value of lambda, it would tell me the length of the vector A times x, where we take our symmetric matrix A with this normalized eigenvector, okay? So if lambda is the largest eigenvalue that there is of this matrix A, if lambda is the largest eigenvalue of A, then I know that the corresponding vector V, okay, or x, that is the direction that A will stretch this vector the most, okay? So the greatest stretching effect that A has is in that direction, because I know that A times that vector is as large as it can be, okay? So we know that the direction in which A will have this greatest stretching effect will be in the direction of that unit eigenvector, x or v or whatever you want to call it, such that that eigenvector is associated with the largest magnitude eigenvalue of A, okay? In the same way, the least stretching effect that this thing has will be in the direction of the eigenvector that has the smallest magnitude eigenvalue, okay? So A will have this effect on these vectors, and it will be some kind of stretching or shrinking, okay? But that all depends on the size on that absolute value of that particular eigenvalue, okay? They've got a good example that looks at this stretching and shrinking and stuff. It's on example 1 on page 417 if you want to go ahead and look at that example. But it does actually display this, and they've got a picture of it as well, which is really, really useful. What does this have to do with anything? Well, singular values are all to do with eigenvectors. And not just eigenvectors, they are to do with eigenvectors of symmetric matrices. Now, not every matrix that we want to decompose into U sigma V transposes we'll get to, not every matrix that we want to decompose in this way is symmetric, okay? We didn't even have symmetric matrices all the time when we tried to decompose it into PDP inverse, okay? When it was symmetric, we could say that it was PDP transpose, which was great, but not every matrix that we want to decompose will be symmetric. So the question is, what do we do about this? Well, just take an n by n matrix A. Okay? If I take A transpose times A, what's the dimension of it? Well, A transpose is going to be n by m, and A is m by n. So that means that this thing is n by n. So it's square. Not only is A transpose A square, but it's actually symmetric. That's due to how you multiply the rows and columns, respectively, of A. Okay? Because the rows of A transpose are actually the columns of A. So, when you do A transpose times A, you're effectively doing column times column of A. And you will end up with this symmetric matrix, okay? If you don't believe me, go ahead and do a small example and you'll see that this is the case. So this is a square matrix, but it's also symmetric, okay? Because of this, we know that this thing must be orthogonally diagonalizable, okay? Because any symmetric matrix is orthogonally diagonalizable, which means that we know that we have these orthonormal vectors, eigenvectors, of this matrix, and we know that we have this diagonal matrix D. Okay, we know it's orthogonally diagonalizable. We know we can write it as PDP transpose. Okay, so let's say V1 through Vn are the orthonormal eigenvectors of A transpose A. Okay, so we know that they're orthonormal to one another, so they all have magnitude 1, and if you take the dot product of any of them, they're going to equal 0. And they form an orthonormal basis of Rn. Okay, they're eigenvectors of an n by n matrix, and there's n of them. And we know that they're linearly independent because they're orthonormal. So we know that they form an orthonormal basis for Rn, and we're going to have these associated eigenvalues, lambda 1 through lambda n. Okay? Now, if I take the magnitude of A times one of these orthonormal eigenvectors, I'm going to take their magnitude and I'm going to square the magnitude. Well, when you do that, okay, you've basically got a vector here, taken its magnitude and squared it. That's the same thing as taking the dot product of this vector with itself. So I can say that this is equal to AVI dot AVI, which is the same thing as saying AVI transpose times AVI, okay? Taking the transpose as a product is the same thing as taking the product of the transposes, but in reverse order. So this is VI transpose A transpose A VI. Okay. Now, we know that each of the VIs are eigenvectors of A transpose A. So A transpose A VI is just going to be lambda I VI. Okay, then rearranging this, I can say that that's lambda I VI transpose VI. I've just taken that constant out the front. Okay, now I know that the magnitude of each of the VI's is 1. Okay, that means that when I take the dot product of VI with itself and then square root it, I'm going to get 1. So VI transpose VI is just the dot product of VI with VI. Okay, if I were to square root it, I get 1. So the square of 1 is just 1. So I know that this thing here is 1. So this is just lambda I. What does that tell me? It tells me that the eigenvalues of A transpose A, number 1 are non-negative because I know that I've taken a magnitude squared here. It's a squared value. Any squared value must be positive. So I know that each of my lambda i's is positive. Therefore, what I can do is I can actually order my eigenvalues. So I can say that I've got, you can order them in such a way, must be n of them. And I'm going to order them in such a way that lambda 1 is going to be my largest eigenvalue and lambda n is going to be my smallest eigenvalue. But every single one of them is greater than or equal to 0. I may have some repeat eigenvalues in there, that's fine, but they all have to be greater than 0 or equal to 0 for that matter. Okay, so I know this about my eigenvalues of A transpose A. What I want to do is relate this back to the matrix A. And it turns out the way that we actually define this is that the singular values, which we've been talking about, the singular values of A are just going to be the square roots of each of my eigenvalues of A transpose A. Okay, so if I come back here, I know that they're all positive, okay, which means I know that I can take the square root of each one of them. So the singular values of A are just the square roots of each of the eigenvalues of A transpose A. So if you are ever asked for the singular values of A, if you're asked for the singular values of A, you go ahead and find A transpose A. That will give you this square symmetric matrix. Then you're going to go ahead and find the eigenvalues of A transpose A. And once you've got the eigenvalues, you're just going to square root them, and that will give you the singular values of A. Okay, so not only that, I'll tell you now, we actually denote each of the singular values by sigma I. It's going to be the square root of lambda I. So not only that, but what does sigma I tell us? Well, if we come back to here as well, I know that if I took the magnitude of A times one of these orthonormal eigenvectors, and then I squared that magnitude, I got this eigenvalue of A transpose A. Well, the square root of this value gives me a singular value because sigma I is just the square root of that value. That tells me that by square rooting both sides of this equation, that the singular values is just the magnitude of A times one of these orthonormal eigenvectors. So each one of the singular values are just the lengths of AVI for every single VI. Okay, so the singular value sigma I is the length of AVI. Okay, it's the magnitude of AVI. Let's go ahead and do a quick example. So I want to find the singular values of this matrix. Okay. If you find A transpose A, okay, transpose this matrix, you get 2, 3, 0, 2. A is 2, 3, 0, 2. And then if you multiply those together, you should find you get 4, 6, 6, and 13. Okay. Now, I need to find the eigenvalues of this matrix. So you go ahead and find the determinant of this matrix minus lambda I. So I'm finding the determinant of this matrix and setting it equal to 0. If you go ahead and find the determinant of this 2 by 2, you should end up with, once you've factored it, I get lambda minus 16 times lambda minus 1. So you do 4 minus lambda times 13 minus lambda and then minus 36. You go ahead, multiply it out and then factor it, and this is what you get. So I get lambda is equal to 1 and lambda is equal to 16. They are my two eigenvalues. Now, remember, just as habit, because you really want to get into this habit because this is how singular value decomposition works, you want to get into the habit of labeling them such that lambda 1 is your greatest magnitude eigenvalue. So that tells me that lambda 1 would be 16 and lambda 2 would be 1. So singular values, I know that sigma 1 would be the square root of 16, which is 4, and sigma 2 would equal the square root of 1, which is 1. Always take the positive, because remember, these singular values tell you the length of AVI, okay, where VI is each of the eigenvectors, those orthonormal eigenvectors of A transpose A. So it's the length of a vector. You can't have a negative length here. So we know that we're dealing with positive values. So take the positive square root. Now, let's say I wanted to find each of the AVIs, okay? I'll tell you now, the eigenvectors of A transpose A, I get V1 is 1, 2, and V2 is negative 2, 1. Now remember, I want to normalize them. I want them to be orthonormal. So if I go ahead and do that, I get U1, we'll call it, is 1 over the square root of 5, 2 over the square root of 5, and U2 is going to be negative 2 over the square root of 5, 1 over the square root of 5. Okay? So now if I take A times U1, I'm going to get 8 over the square root of 5 and 4 over the square root of 5. So you can go ahead and multiply this vector here by A. Okay, so I've done A times that vector. And then in the same way, if I do A times U2, what I actually end up with is negative 1 over 5 and 2 over 5. 2 over the square root of 5. So if I go ahead and find the length of each of these vectors. Okay, so I'm finding the length of AU1 and the length of AU2. Okay, all you do is you square each of the terms in the vector. So I'm going to square this and square this, add them together, take the square root. So if I square 8 over the square root of 5, I would get 64 over 5. And if I square 4 over the square root of 5, I get 16 over 5. That gives me 80 over 5. If I go ahead and, that's actually 16. If I go ahead and square root 16, I get 4, which is the singular value that is associated with U1, because I had sigma 1 was 4. So each one of these, if you went ahead and did this for AU2, you would find that the length of AU2 was 1. So each one of these singular values tells me the length of A multiplied by that orthonormal eigenvector of A transpose A. Okay. Now, if you actually look at these vectors here, so I've got 8 over the square root of 5, 4 over the square root of 5, and negative 1 over the square root of 5, and 2 over the square root of 5. Do you notice anything about these vectors? If you take their dot product, okay, I would get negative 8 over 5 plus 8 over 5. I get 0. these vectors AU1 and AU2 are actually orthogonal to one another. And that is actually not a coincidence. Okay? We're going to do a theorem here with a proof, and the proof isn't particularly short, but if you bear with me. Let's say that I've got an orthonormal basis for Rn that is made up of those eigenvectors, those orthonormal eigenvectors of A transpose A. So I'm going to say that V1 through Vn is an orthonormal basis for Rn made up of orthonormal eigenvectors of A transpose A. Okay, so each one of those is an eigenvector for A transpose A, and I know that each one has magnitude 1. Now I'm going to arrange V1 through Vn such that the associated eigenvalues go in decreasing order. So I'm going to arrange V1 through Vn such that the associated eigenvalues go in decreasing order. Okay. Get into the habit of doing that. It just makes things work out nicely with singular value decomposition. Okay. So I'm going to arrange them in this order, and I'm going to suppose that A has R non-zero singular values. Okay. So some of these eigenvalues of A transpose A may be 0. So when I square root them, I'm still going to get 0. But I'm going to assume that R of them are non-zero. Okay. Then, if I take A times VI for any one of these VI's where I get a non-zero singular value, so a non-zero eigenvalue, and I take A times VI, each one of those AVI's is going to be orthogonal to one another, and it actually forms an orthogonal basis for the column space of A. So if this is the case, I've got R non-zero singular values, which means that I must have R non-zero eigenvalues for A transpose A. Then, if I take A times each one of the associated VI's for those R non-zero singular values, those R non-zero eigenvalues of A transpose A, then those form an orthogonal basis for the column space of A. And therefore, if they form an orthogonal basis for the column space of A, the dimension of the column space of A, being the rank, okay, the rank of A, therefore has R elements in it. Okay, so if I know that A has R non-zero singular values, I want to show that not only do these form this orthogonal basis for the column space, but that then tells me something that we looked at a few chapters back. We could look at the rank of A, and the rank of A actually turns out to be R, where we have these R non-zero singular values. Okay, I'm going to go through the proof of this. It's not short, but most of it is pretty much like what we've done before. It's very algebraic. Okay, so to prove this, I'm going to start out with the fact that I know that each of the VI's are orthogonal to one another. So I know that VI and VJ are orthogonal if I does not equal J. So that tells me that VI dot VJ equals 0. Now, That means that if I were to take AVI transpose times AVJ times AVJ, that's going to give me, remember when you take the transpose of a product, you just take the product of the transposes in the opposite order. So that's going to give me that, okay? Now, again, we've said this before. This thing here is just going to equal lambda j vj, because each of the v's are going to be the eigenvectors of A transpose A. So I know that this is going to be lambda j vj. I can then pull that lambda j out the front. So that's going to give me lambda j vi transpose vj. Now this thing is going to be 0 because I know that this is vi dot vj. That must be 0 because each of these is orthogonal to one another. They're actually orthonormal to one another. So I know that this thing is going to equal 0. Therefore, I get 0. So that tells me that each of these is orthogonal to one another when I have a distinct vi and vj. So when I doesn't equal j, I know that this thing is going to be orthogonal. So I know from that that AV1 through AVN is an orthogonal set. Okay. Now, I know that the lengths of each of these vectors, okay, because AVI is going to be a vector, I know that the length of each of these is the associated singular value sigma I. So, let's say that there are R non-zero singular values. Okay. If there are R non-zero singular values where the singular value is actually the length of each of these vectors, then I know that there are R vectors that have non-zero length. Okay? The only way that they would have non-zero length is if they themselves were non-zero. Okay? As soon as AVI, for some VI, as soon as AVI was 0, it's going to have 0 length. The associated singular value is 0. So it only has a non-zero singular value if it itself is non-zero. So that would tell me if I have R non-zero singular values, that tells me that AV1 through AVR, for some R, however many non-zero singular values you have, that means that these are the orthogonal vectors that are non-zero, okay? Because they're orthogonal, it means that they are linearly independent. So I have a set of linearly independent vectors here. I have R of them, and they span the column space of A, okay? Why do they span the column space of A? Well, let's say we know that V1 through Vn was a basis for Rn. Okay, it's a basis for Rn, and it is actually this orthonormal basis for Rn. Okay, because it's a basis for Rn, I can write any vector in Rn as the sum of a linear combination of these vectors. Okay, that means if I take A times X, I'm going to get this. Now, we've said this before. There are R non-zero singular values. There's only R that are non-zero. The rest of them, R plus 1 through N, for some I, that's R plus 1 through N, the rest of those singular values are going to be 0. So any of these AVIs that are associated with sigma I, where sigma I is 0, is going to give me a 0 AVI. So I know that is equal to that, because any other entries after that, so CR plus 1, AVR plus 1, that's going to be 0 because AVR plus 1 is 0 because its associated singular value is 0. So I know this is in the column space of A, okay, because all this is a linear combination of the columns of A. So I know that the column space of A is spanned by AV1 through AVR. They're linearly independent because they're orthogonal, as we've shown before. So that tells me AV1 through AVR form a basis for the column space of A. And not only do they form a basis, they form an orthogonal basis, because I know that if I take AVI dot AVJ, I'm going to get 0. So they actually form an orthogonal basis for the column space of A. Okay? Because there's R of them, it tells me, therefore, as the basis for the column space of A has R elements in it, that the rank of A must equal R. And that's the end of the proof. So it's not the easiest proof, but you can do everything in there. Now we're going to use these singular values that we've been talking about to decompose that matrix A. Okay, that's what's going to give us this thing called the singular value decomposition. We tend to denote this by SVD, okay, singular value decomposition. And the way that we will actually decompose this matrix is by saying that we have U sigma V transpose. Okay, now sigma, okay, if A is M by N, then sigma is also going to be an M by N matrix. But the way it's actually going to be set up is such that we have this diagonal square matrix from the top left-hand corner. So you'll have this diagonal matrix in the top left-hand corner of sigma, and any other entries in sigma are going to be 0. Okay, so you'll see this when we do it, but you're going to come up with this diagonal matrix D, okay? And we'll go through how to do that. And then any other entries to make up the M by N entries in sigma are going to be 0, okay? Then we're going to have these two matrices, U and V. Each one of them is an orthogonal matrix, which means it's an orthonormal matrix that is square. U is going to be M by M, and V transpose in that case is going to be N by N. Okay, so the question is, how do I find U, sigma, and V in order to find this singular value decomposition of a matrix A? I'm going to do this by an example because it's the easiest way to see this. When you actually find U, it's not the easiest thing in the world. I would not make it this complicated for you on a test because there are so many steps to it. If I did this, I would lead you up to it. So you would already have this information beforehand, but it actually involves, to find U, you've got to do the Gram-Schmidt process, which in itself is a long process anyway. So I would lead you up to it. So I would ask like a Gram-Schmidt process problem. And then when I ask you to do the singular value decomposition of a matrix, you would actually be using the exact same vectors that you found in the Gram-Schmidt process from before. I wouldn't come up with a new one. Okay, so I would kind of lead you into it. So for this example, I want to find the SVD of A is equal to 1, -1, -2, 2, 2, -2. So I want to find the singular value decomposition of this matrix. So I need to find U, sigma, and V. Okay. The easiest things to find are V and sigma, as we'll see. But in order to do this, I'm going to do this step by step. So you're going to follow these steps when you go ahead and do this. When you find this, the first thing you're going to do is to find A transpose A, its eigenvalues, and normalized eigenvectors. Okay, so A transpose A. Okay, so you're going to transpose this matrix A and multiply it by A. When you do that, the matrix that you end up with is 9, negative 9, negative 9, 9. Okay, go ahead and find the eigenvalues and eigenvectors, and then once you've found the eigenvectors for each one, you're going to normalize it. So you're going to divide it by its magnitude. Okay, so if you do that, you should get lambda 1 is 18, lambda 2 is 0. So again, make sure when you do this that you always label lambda 1 as your largest eigenvalue, and then you're going to go in decreasing order. Okay, then if you go ahead and normalize the eigenvectors, the first eigenvector is just 1, negative 1. So if you go ahead and normalize it, you get 1 over the square root of 2, negative 1 over the square root of 2. And then you're going to get V2, which would have been 1, 1. So you go ahead and normalize it and get 1 over the square root of 2, 1 over the square root of 2. Okay, so that's always your first step. Now we can go ahead and start finding those matrices and see what they actually are. So the second step is to set up V and sigma. Okay. So when you do this, V is just a matrix whose columns are those normalized eigenvectors of A transpose A. Okay, but make sure you get them in the right order when you do this. Okay, so the first column of V is the eigenvector, the normalized eigenvector of A transpose A that is associated with the largest eigenvalue of A transpose A. Okay, so the first column of V is going to be this normalized eigenvector because the associated eigenvalue is the one of largest magnitude for A transpose A. Okay, and you're going to go in order such that the associated eigenvalues go in decreasing order. Okay, so that tells me that V is going to be 1 over the square root of 2, negative 1 over the square root of 2, and then the second column is the normalized eigenvector associated with lambda is equal to 1. Okay, lambda is equal to 0, sorry. Okay, so then my second column was this because lambda is equal to 0 was my next highest eigenvalue. Okay, so once you've got V, so V is actually pretty easy to get. Okay, once you have that, we then need to find sigma. And the way that you find sigma is first to find these singular values for A, okay, which is the square root of each of the eigenvalues for A transpose A. So I know that lambda 1 was 18 and lambda 2 was 0. So that tells me that sigma 1 is the square root of 18, which is 3 times the square root of 2 if you simplify it. And sigma 2 would just be the square root of 0, which is 0. Okay. Now, sigma must be a 3 by 2 matrix because A was a 3 by 2 matrix. So what I'm going to do is I'm going to create a diagonal matrix where I have the singular values on the diagonal. Okay. So I'm going to start out with that. So I'm going to create this diagonal matrix where I have the singular values on the diagonal. And they are going to decrease in magnitude as you go down the diagonal. So the first singular value should be the largest singular value. Okay. So your first singular value, your first entry should be 3 root 2. And then your next highest one is 0. You then make a diagonal matrix out of that. Okay, it is a diagonal matrix. It just has a 0 on the diagonal because you have a 0 singular value. Okay, so you work your way down through the singular values, writing them down and creating this diagonal matrix. Okay, once you have this diagonal matrix, you look at the dimension of it. So far we have a 2 by 2 matrix, but I want sigma to be 3 by 2. Any other entries in that matrix to make up the dimensions will be zeros. So I'm going to have a 0 here and a 0 here. Okay, that makes it a 3 by 2 matrix, and I've got that diagonal matrix in there where the entries on that diagonal are the singular values of A. They are the square roots of the eigenvalues of A transpose A. Okay. So the next thing we need to do is go ahead and set up U. Okay. So this is the most difficult part of all of this. Okay. Finding V and sigma are pretty easy. This is the most difficult part. If A is M by N, okay, we know that sigma is also M by N, and we know that V is N by N, which means that U is M by M. So in our case here, that means it must be this 3 by 3 matrix. Now, I'm going to tell you how to find U, and then we're going to talk about it and figure out what we need to do for this specific example. So, when A has rank R, the first R columns of U are the vectors AV1 through AVR, but normalized. So, let's think about this. If A has rank R, that means that we know that it has R non-zero singular values. Okay? So in our case, we had 2 singular values, but one of them was 0. So I only have one non-zero singular value, which from our previous theorem tells me that the rank of A is just 1 for that one non-zero singular value. Okay? So whatever your rank of A is, the first R columns, so this tells me that the first column of U are the vectors AV1 through AVR, but normalized. So I'm taking my matrix A, my original matrix, I'm multiplying it by each of the columns in V, but only the first R columns. Okay? So if I've got, let's say, 3 non-zero singular values, I'm going to do AV1, AV2, and AV3. So I only do it for those vectors VI, such that their corresponding singular values were non-zero. Okay? So once I've done that, I then normalize those vectors. Now in my case, the rank of A is 1, which means that I only need to go up to AV1. Okay? So that tells me that I'm going to do my matrix A, which was this matrix here, and I'm going to multiply that by my vector V1. So I'm going to do A multiplied by V1. And if I do that, A times V1, I'm going to get 1, -2, 2. But I also need to remember that I need to normalize this vector, which means I need to divide it by its magnitude. Now I know that the magnitude of each of these AVI vectors is just sigma I. So when you do this, when you normalize these, you just divide each one of them by that non-zero singular value. So I know that I only do this for those AVIs such that the corresponding sigma I is non-zero. Because if sigma I is 0, well, I'm dividing by 0, so it doesn't work. So I know that here, if you work this out, if I do A times V1 divided by sigma 1, I get 1/3, negative 2/3, and 2/3. Okay, if you go ahead and work that out. Now, I already know, as I said, AV2 is 0 because sigma 2 was 0, so I'm not going to use that as a column of my matrix in U. If you end up with having n non-zero singular values, okay? So if I've got m non-zero singular values, in this case 3 non-zero singular values, that would mean that each of my columns corresponds to the normalized AV1, the normalized AV2, and the normalized AV3. So if I have the correct number of non-zero singular values, I have my whole matrix U filled. That's really easy, okay? Because all I have to do is exactly what I've done here, and I've got the whole matrix. I've got my whole 3x3 matrix if I've got 3 non-zero singular values. But I don't have that in this case. I only have one of them. So the question is, where do I get my other 2 columns from in this case? Well, I want U to be an orthogonal matrix, which means that its columns have to be orthonormal to one another. Okay, they have to be orthogonal and they have to be orthonormal. Okay, you want them to have magnitude 1. Let's start off with the whole orthogonal thing. Okay, I want these vectors to be orthogonal to one another, which means my other 2 columns have to be orthogonal to this one. If they are orthogonal to that, it must mean that if I take the dot product of this vector with any other vector in that orthogonal space to this, I should get 0. So let's say I'm going to take x, and I'm going to let x be x1, x2, x3, be orthogonal to, I'll call this U1. Okay, it's my first column of U. Okay, so my other 2 columns, I need them to be orthogonal to U1. So I'm going to look at that space, that whole space. It's going to be a plane that is orthogonal to U1, and then I'm going to look at the vectors that span that space. Okay, and out of that, I want 2 vectors that are orthogonal to one another. Okay, but first of all, let's focus on this space that is orthogonal to U1. So any vector in that space has to satisfy U1 dot x is equal to 0. Okay, any vector x in that space should satisfy that. So if I do that, if I take the dot product of this vector U1 with x, I'm going to get 1/3 x1 minus 2/3 x2 plus 2/3 x3 is 0. If you simplify that and multiply both sides through by 3, what you end up with is x1 minus 2x2 plus 2x3 is 0, if you simplify this. Now, if I go ahead and solve, okay, you can treat x2 and x3 like free variables. Okay, you've just got one equation in 3 unknowns. Okay, so that means that my solution x can also be rewritten as this. Because, okay, if I look at x1, x1 is 2x2 minus 2x3. So x1, okay, my first line here, has 2x2 minus 2x3. x2, my second line, just has one x2 in it. It's got no x3s. And then finally, x3 just has one x3 and no x2s. So that tells me that these 2 vectors form a basis for the space that is orthogonal to U1. So that's great because both of these vectors are orthogonal to U1, and that's great. You would think we're all good to go. But the problem is these two are not orthogonal to one another. So let's call them W1 and W2. Okay, so I've got these two vectors. They're in that space orthogonal to U1. That's great. But now we want an orthogonal basis for the space that these two vectors span. Okay, so these two vectors are a basis for this space that's orthogonal to U1 right now. Okay, they're a basis for that plane. But I want them to be an orthogonal basis. Whenever you hear orthogonal basis, think Gram-Schmidt. Okay, whenever we needed an orthogonal basis for a space, that was the method that we used. So what you would go ahead and say is, okay, I'm going to take, we'll call it, I don't want to get confused with variables here. Okay, let's call it S1, okay? S1 we always take as our first vector, which would be 2, 1, 0. And then you can go ahead and find S2, which would be W2 minus W2 dot W1, or S1, I should have said, over S1 dot S1 times S1. So you can go ahead and you can find that orthogonal projection of W2 onto the space that's spanned by S1, and then you find the vector that's orthogonal to that, and so then you find S2. So if you went ahead and did this, S1 and S2 would be orthogonal to one another, okay? And the vector that you get out from doing that then has to be normalized, okay? So when you do this, you're going to go ahead and you can normalize this vector, and you can normalize the vector that you would get from this, okay? The vector that you get here is -2, 4, 5. So these two vectors are orthogonal to one another. They're just not orthonormal, okay? Because Gram-Schmidt will only do orthogonal. It won't calculate an orthonormal vector for you. So once we've got this, we have to go ahead and normalize them. So when you do that, I get U2 is 2 over the square root of 5, 1 over the square root of 5, 0. And U3 is going to be -2 over the square root of 45, 4 over the square root of 45, and 5 over the square root of 45. So that tells me that my matrix U, okay, let's come back. My first column of U was this one here. It was found by normalizing AV1, okay? Then what I did was, because I had to have two other vectors that formed this orthonormal matrix, and not just orthonormal, it was orthogonal because it's square. It formed this orthonormal basis, so each of the columns have to be orthonormal to one another. So what I did was I found the space that was orthogonal to this vector. I found two vectors that span the space that was orthogonal to U1, and the vectors that were orthogonal were this and this, and I just did that by solving a formula, by using that property of orthogonality, okay? So these two vectors are a basis for the space that is orthogonal to this vector, which is great, but the problem is that they are not orthogonal to one another. So I had to go ahead and do Gram-Schmidt to find two vectors that form a basis for that same space, but they're orthogonal to one another. So now this vector, and this vector are all orthogonal to one another. This vector has already been normalized, but I have to go ahead and normalize these two vectors so that not only are all three vectors orthogonal to one another, they're orthonormal to one another. So when I do that, my final matrix ends up being these three columns put together. And so with what we found, A is equal to U sigma V transpose from those three matrices that we found. Okay. As I said, finding U is the most difficult part of all of this. V and sigma are very easy. V is just going to be those orthonormal eigenvectors of A transpose A. You put them in a certain order such that the associated eigenvalues decrease in magnitude, okay, as you go along. And then sigma is created with this diagonal matrix that's made from the singular values of A, and then you fill in the rest of the matrix with zeros. When you get to U, okay, you would hope here that you had 3 non-zero singular values. If you have 3 non-zero singular values, then those 3 columns of A are just going to be formed from the normalized versions of AV1, AV2, and AV3. The problem here is that the only one that you have is the first one, okay? It's only the first singular value that is non-zero. So we only know one column of U, which is the normalized version of AV1. The other 2 columns we do not know. So we had to go ahead and find that space that was orthogonal to U1, and then find an orthogonal basis for that space, and then normalize those vectors that formed that orthogonal basis. Okay, and that gave us those 3 columns of U that we found. Okay, and that gave us that U sigma V transpose was equal to A. As I said, it's not the easiest thing, and if I gave you anything like this, I would give you a lot of lead up. I wouldn't just spring a problem like this on you, because there's a lot of other processes involved. Like, you've got to deal with A transpose A at one point, you've got to deal with Gram-Schmidt at another point, you've got to deal with normalizing vectors. There's a lot going on here. So I would give you a lot of lead up as opposed to just asking the question if it involved this much work. If you had 3 non-zero singular values here, this would have been way easier, and finding U would have been easier. Okay, it's just with this particular problem there was more to it. Why do we like SVD? There's 2 reasons that I'm going to talk about here. One's got some more stuff to it that we're not going to do in this course, but it's a lot to do with modeling. Okay, a lot of times when you have a system, AX is equal to B, so you've got this linear system that you want to solve. The problem is when you go ahead and try some Gauss-Jordan row reduction on the augmented matrix AB for AX is equal to B, when you go ahead and do this Gauss-Jordan row reduction on AB, you run into the problem that when we do Gauss-Jordan row reduction, at some point you normally end up dividing a row by a number so that you can get that pivot of 1. Okay? Problem is, when you divide by a number there, you can run into the situation with some of these like more complicated linear systems that we don't get to. You come up with a situation where you actually end up dividing by a number that is incredibly close to 0. If you divide by a number like that, all of your other values shoot up towards infinity. Okay? That can cause a lot of problems and a lot of instability within your system. Okay? Because you don't want to be divided by anything that's close to 0. So what they actually do, they do this SVD on this matrix A. Okay? So they'll take A and they'll construct the singular value decomposition of it. You can actually tell from the singular values, if they are very, very close to 0, then you're going to run into problems in A. When you try and solve this, A times X is equal to B. So before they go ahead and try and solve some of these systems, they actually go ahead and see what this decomposition is. If they have these really weird singular values that are especially close to 0, then they know that they're going to end up dividing by something close to 0 when they go ahead and do this solving AX is equal to B. So they know that they're going to run into problems and that the system is unstable. So that's why it's useful in terms of modeling. In terms of what we've been talking about, I'm going to tie it back to something that we did a very long time ago. And it's our 12-part invertible matrix theorem. And I've got to cover something else very quickly and explain something very quickly, but it shouldn't be too difficult in order to get to this. but I'm actually going to give you some extra parts to that invertible matrix theorem that are true for any invertible square matrix. Okay. So, I want to talk about two things. And that is these two. Okay. The first one is easier to see, and once you see the first one, you'll get the second one. Why is this true? Well, if we look at a times x is equal to 0, okay? Any x that satisfies this is in the null space of A, okay? When you multiply a times x, the way that we do matrix multiplication, you do row times column. So what I'm doing here is I'm taking a row of A and I'm taking the dot product of that row with x, because I'm multiplying the associated entries of that row of A with that particular entry in x. So I'm taking a dot product of a row of A with that column x. Okay. When I do that, I've got to get 0 with every single row of A. So what does that tell me? If I take the dot product of every row of A with x and get 0, that tells me that for every x that is in the null space of A, it must be perpendicular, it must be orthogonal to every row in A. So the row space of A is orthogonal to the null space of A. Okay. Similarly, if I were to take A transpose, okay, and solve A transpose x is equal to 0, any x that satisfies this is in the null space of A transpose. But now, my rows in A transpose were my columns of A. So, what I am doing here is I'm actually taking a column of A, being a row of A transpose, I'm taking a column of A dotted with this x that is in the null space of A transpose. And when I do that, I get 0. So that tells me that the column space of A is perpendicular, it's orthogonal to that null space of A transpose. Okay? Why do we want to know about this with our singular values? Well, if you think about it, okay, the first R columns of U, okay, being U1 through UR, that are associated with those R non-zero singular values, okay, that means that each one of these is a normalized version of AVI. That means that each one of these is in the column space of A. Not only is it in the column space of A, we actually proved before that AV1 through AVR actually form a basis for the column space of A. So U1 through UR, where we have R non-zero singular values, they actually form a basis for the column space of A. Okay, we did that before when we showed that AV1 through AVR formed a basis for the column space of A. What does that tell me? Well, coming back up here, okay, that must mean that if they form a basis for the column space of A, then the remaining U's, okay, that are in that matrix, so UR plus 1 through UN, or UM, sorry, okay, UR plus 1 through UM must form a basis, okay, bearing in mind that they must be orthogonal to these vectors here, okay, because that was by construction, they're actually orthonormal, which means that they're orthogonal to those vectors. That must mean that these vectors here form a basis for the null space of A transpose. Okay. So I've got a basis for the column space of A, and by taking the vectors that span that m minus r plus 1 dimensional space, they must be a basis for my null space of A transpose. Okay. So I know that. Coming back as well, okay, I'm going to go ahead and use another formula that we had. Okay. So I know that I selected to have UI being the normalized version of AVI, which was just dividing AVI by its magnitude being the singular value sigma I. Okay. And that worked for the R non-zero singular values, because if you had a zero singular value, you couldn't do this. But that meant that for the other singular values where sigma I was 0, okay, that told me that for R plus 1 through n, AVI was 0, okay, because its singular value was 0, okay. So that means, because sigma I was 0, that must mean that this thing has length 0, which we talked about before, which means that AVR plus 1 through AVN must be a basis for the null space of A. Okay, they actually form an orthonormal basis for the null space of A. Okay, and the space that was orthogonal to that, were the vectors V1 through VR. And we set up here that the row space of A was orthogonal to the null space of A. So that tells me that V1 through VR, those first R columns of that matrix V, form a basis for row A. Okay. So each one of these, they're actually not just a basis, they're not just an orthogonal basis, it's actually an orthonormal basis. Okay. So each one of these vectors has magnitude 1, and they're actually all orthogonal to one another. Okay. So why is this useful? Well, let's go back to our invertible matrix theorem. Okay. If A is an n by n invertible matrix, okay. If A is an n by n invertible matrix, okay, we've looked at a ton of this before as to it's got to have linearly independent columns, etc., etc. Like there was a ton of stuff that we had. There were 12 different properties that we had. We now have 4 extra properties that we can look at. Now, if you remember, one of the parts to the invertible matrix theorem was that the column space of A was Rn. So let's go back and look at what we had. Well, the column space of A had basis U1 through UR. Okay, that would mean that there were only R vectors in its basis. But if the column space of A is equal to Rn, that means it must have n vectors in its basis. So that tells me that I must have n non-zero singular values in order for this invertible matrix to actually be invertible, okay? Otherwise, it's not going to be invertible if there are less than n singular values, because it means that I'm not going to have enough vectors here that are going to be in my basis for the column space of A. So the first thing that we have is that A has n non-zero singular values. Now, the next thing, again, if we now have n non-zero singular values, which means we have all n of my u's in here, that must mean that this is completely empty. There's nothing in there apart from the 0 vector. So that must mean that the null space of A transpose is 0, okay? Which means that the space that is orthogonal to the column space of A, being the null space of A transpose, is just 0. There's nothing in it because the column space of A is all of Rn. So that must mean that I've got nothing in the null space of A transpose. Now, the next thing that I want to look at is the null space of A and the row space of A. So, again, I now know that for an invertible matrix, I must have n non-zero singular values, which must mean that I must have V1 through Vn all in here. So I'm going to have only the 0 vector in here. So the row space of A has got n vectors in its basis, meaning that the row space of A is equal to Rn. So it's not actually just the column space of A that is Rn, it's actually the row space of A is also Rn. But if that's the case, then I know that the null space of A has nothing in it. It's just the 0 vector, which is exactly what we have said before, okay? When A is invertible, I know that the only solution to A times x is equal to 0 is the 0 vector. So this goes along with exactly what we have said before. The only thing I want to add to this is because we know that the row space of A is perpendicular, it's orthogonal to the null space of A. I can also write this as the row space of A with uptack is going to be the null space of A, or the null space of A uptack is equal to row A, which would be Rn, okay? So it can be written either way, but we know that the null space of A is just the 0 vector here. So if I take anything that's orthogonal to that, well, 0 dotted with any vector is going to give you 0. So I know that the space that's orthogonal to the null space of A is Rn. Okay, so this gives us an extra few things to add on to our invertible matrix theorem that we've kind of been working on through this whole course. Okay, I know that this isn't the easiest chapter and there is a lot going on here when you do that singular value decomposition and then adding some more things onto the invertible matrix theorem at the end. But if you do have any questions on it, please let me know and I am more than happy to help. And let me know if you need any help with the review too.